Okay, any questions? Okay, so we're talking about finding the Galois group specific polynomial. And here was like kind of the last takeaway from last time. If you have a polynomial and it's separable and irreducible, and say at degree n over the field k, then it's got some splitting field, which we'll call f. The Galois group of f over k, which I will call the Galois group of this polynomial. So it's when you see Galois group of f of x, what you mean is the splitting field of this polynomial. It turns out to be a transitive subgroup of this n, where n is the degree of the field. This is why. So one thing to kind of keep in mind, although it's perfect, but I like to keep in mind like sort of thinking about splitting fields of polynomials over Q, because that's a good kind of baseline thing. But of course, this is all of what we say is true in this more general sense here. But for example, in characteristic 0, this is why the quadratic formula is so easy, right? Because the only transitive subgroup of S2 is Z-2, right? So small number of automorphisms, you can easily kind of control this. So let me give you kind of some facts that I've given for example. S2 is only transitive subgroup S3 and A3 are transitive subgroups, the only transitive subgroups of S3. So if you've got an irreducible cubic, now you've got two choices for the Galois. The cubic form is a little tougher. For S4, transitive subgroups are isomorphic. S4, A4. Let me point out what this is true for any Sn. That is to say that if you have any n bigger than 2, bigger than or equal to 2, then A, n, and Sn are both transitive subgroups of Sn. So you're going to get these two automatically. It turns out that if you have any 4 cycle in the group, it has to be transitive in S4, because just taking powers of that 4 cycle, you can take any element to any other element, right? So anything that contains 4 cycles. So for example, cyclic of order 4, dihedral square. And I do mean isomorphic too, because for example, well, these groups can have sort of isomorphic copies. And not all Z2s work. The one that I mean here is the one here to transit. This is certainly a subgroup. By the way, it's not clear immediately, I don't think, that this is actually a subgroup. Like, is this times this really this? But if you check it, you'll see that this is in fact a subgroup. And this was transitive because given any A and B, I can find one of these little cycles here when we take A and B, right? If I had the subgroup, have it here. If I had the subgroup, let me make a kind of a note over here so you don't confuse it. This is also a subgroup of S4, right? It's isomorphic to Z2, Z2. But this one's not transitive because, for example, there's no way to take the element 1 to the element 3, right? So this one's got the extra which you need. Yeah, of course, these two subgroups are isomorphic, but they're not conjugate. And 1, 2, 3, 4, that's it. For S5, the transitive subgroups are isomorphic too. S5, A5, cyclical order 5, dihedral on 5 dot, and the Frobenius group order 20. There's a subgroup that's generated by a 5 cycle and 2 cycle. And in fact, from our homework, the Galois group with x fifth minus 3 is actually has Galois group Frobenius group of 20 elements. And again, let me know, by the way, can somebody tell me how many elements of order 5 are there in S5? Right now. Well, think of this way. If you want to find an element of order 5 in S5, it has to be a 5 cycle. Agreed? Okay. And that 5 cycle can start with 1 because if it doesn't just cycle through until it starts with 1, right? Because 5 is prime, you don't have to worry about any of that stuff. So does that help you determine how many there are? Right, there's 24 of them, right? Because now you've got complete freedom on the other 4 entries. You got in and all in. So there's 24 elements in S5 of order 5, right? That means there's 6 CeLO 5 groups, right? Because in clumps of 4, they correspond to a cyclic subgroup of order 5. So there's 6 of them. So when I say isomorphic, there's actually 6 of them here, right? But not S5, I'm sorry. Cyclic of 5, there's actually 6 of them. There we go. Okay. Any questions? By the way, 1, 2, 3. This one, you can check it out. I believe it's generated by Frobenius group. 20 elements is generated by those two. That 5 cycle, that 4 cycle. This gets out of hand pretty fast. There are 16 up to isomorphism. Up to isomorphism, there exists 16 transitive subgroups of S6. All right, so that's a taller order. There exists 7 transitive subgroups. 7. So it calms down a little bit. 7 is prime, and that's important there. But when the number becomes more and more composite, so to speak, or with lots of prime factors, there's 50 yes, 8, and there it is. You don't know the risk of this one because 301 transitive subgroups, that's 12. So if you have an irreducible polynomial, say over Q of degree 12, there's lots of choices. Yeah, what? So I want to define something here called the discriminant, which is going to be useful for cubic polynomials in particular. It's useful for all polynomials, but we're going to use it for cubics, and we're going to get our for extensions of cubic, we're going to wrap our head around polynomial degree formula class. So definition 853. Let K be the field, and suppose that the characteristic K is not equal to 2. So it can be any characteristic except 2 here. Suppose that degree of the F is n. Let's see, F fast. K fast. N. And suppose that F has indistinct roots of some splitting field K. And suppose F has indistinct roots in some splitting field F, or yeah, a little f over K. We define delta this is a little gadget where we take the roots and put them in some order. Take all possible differences in roots. So take all these roots and list them in some order. So just make a list of them. There should be all of them distinct. And of course, you can see what we need. We need them distinct because if they're not distinct, this product will turn out to be zero, right? So you list the roots and just one index I less than j go through this right here. This thing is called delta, and we define the discriminant is the square of this. So it's the product of these squares. Now, what's the important thing here? Well, this proposition here. By the way, I'm gonna focus for this little kind of computational applied section. I'm not going to focus on proofs really. I'm going to focus on well, really more examples and results here, how to use this. However, if you want to go over the proofs, we can do that. Proposition. Let B be A. Oh, by the way, I'm going to use the this delta squared, which is the discriminant. D is in K, and delta is in K if and only if the Galois group and remember the Galois group for f of x, what we mean by that is the Galois group of the splitting field of this polynomial over K is contained in A and N. So really what that means is, so the statement says that this square is always in K. In fact, you should check that out. That's kind of the easiest thing. let me get you started, the first part here. Remember the old quadratic formula here, right? So if you look at R1 minus R2, this is equal to this minus this, so it's going to be right. So in this case, which is in the field, but this actually works in general, and you might want to convince yourself of that. And let's go a step further. This means that deltas in K, if and only if the Galois group is contained in A and M, right? Well, for quadratics, this is kind of a simple conclusion here, right? Because what happens when what happens when the square root of this is contained in the field? Think of, say, rational numbers. That means that this thing is already a square, and that means this is contained in A2, and A2 is the identity, which means things already in the field in the first place. Let me give you an example here, kind of a work example. You might actually, I'll work through this myself, and it's a bit grungy, but it's not terrible. Work through this for fun. That's what I do for fun. The cubic polynomial x cubed plus ax squared dx c. So if you have a cubic polynomial at this point, the discriminant is given by see if I get this all right here. A squared b squared minus 4b cubed minus 4a cubed c minus 27 squared plus 18a c. By the way, this is kind of a good sort of exercise. Let me get you started on how you would figure this out. The cubic is mono, so that's how it should factor, right? There's 3 roots. And so you get these identities like, for example, well, so what you get here is this is x cubed minus R1 plus R2 plus R3 x squared plus R1 R2 plus R1 R3 plus R2 R3 x squared drops by x minus R1 R2 R1. If you multiply this out. Right. Now, even though you don't know what the roots are, see if you can use that in this formula here and figure out what the discriminant is. It's actually not too bad, right? I mean, it's grungy and you gotta troll through it, but you can get this formula here. Because, for example, you know the sum of 3 roots has to be negative a, right? And this product here has to be b and so forth, and you can leverage that into figuring out what the discriminant is. But for now, we'll just kind of take that as given. So let me give you a concrete example. So if we have if we have the specific polynomial x cubed minus x plus x squared minus 2x minus 1, and I'm going to repeat this as a polynomial cube, then the discriminant if you plug those numbers in, right, namely a is 1, b is minus 2, and c is minus 1, you should get, if I did this right, discriminant of 49. And this tells you for cubics, this tells you basically everything you need to know, because for cubics, there are only two choices from Galois, right? One of them is S3, and the other one is A3. And this proposition tells you what you know. If that discriminant is, so if the square root of that thing so the Galois group of x cubed plus x squared, that's A3. So the discriminant, either its square root is in your base field or it's not, and that's all you need to do to tell what the Galois group is. So, by the way, without looking, I can tell that polynomial must have three real roots. How come? And I know this from the Galois group. Can anybody tell me why? It was something like that. So the Galois group is A3 because the discriminant is 7. Right? So if you believe that theorem, the Galois group is A3, right? What happens to cubic polynomials? How many roots can they have? Say you've got an irreducible cube. Right, it can have. So as far as real roots go, so this is polynomial of a cube. As far as real roots go, how many real roots do you have?
One.
You've got 1 or 3, right? Because the complex roots that are not real come in conjugate pairs. Agreed? So I claim that this thing has 3 real roots, so it can't have complex conjugate pairs. Can somebody explain why? I know that. Yeah.
Conjugation would be a non-trivial.
That is correct. That is correct. So if there were a pair of complex roots that are not real, then complex conjugation would be a non-trivial automorphism of that field. Everybody agree with that? And complex conjugation has order what? As an automorphism, it's got order 2, right? You conjugate, you unconjugate, right? There's no element of order 2 in A3, so it has to have 3 real roots. Right? I'm going to generalize that observation later. By the way, be careful. Just because it's got 3 real roots does not necessarily mean that Galois group is A3, because I could have another. If I had 3 real roots, I could have another automorphism that permutes just the two of the real roots. That's a possibility. At this point, that's a possibility. But the knowledge I have going in is what the Galois group already is. Yes.
So, but the theorem, like the Galois group is like less than equal to A, and how do you know here is actually it's not something small?
Because the only transitive subgroups of S3 are S3 and A3.
Oh.
It's because the list is so freaking short, right? I ran out of real estate. Okay. Now we're gonna deal with cortex now. I always think of this over Q, but you can do this over any field as characteristic not equal to. So here's my setup. So for cortex, let me show you some fun stuff here. And I'm going to use one of the transitive subgroups of S4 as a tool here. So let me give you the ground rules for this. Let B be transitive prime 4 subgroup of S4. So B is the one that I listed earlier. Let K be a field. Again, I want the characteristic K to not equal to. And F an irreducible polynomial of degree 4 with distinct roots in that. Oh. Here's my player. F of X and KX. We'll send that F of X has distinct roots in a splitting field, which I'll call F. So in particular, polynomial is 4. And I should have said this earlier, and F of X is irreducible. Oh, didn't even say this. All right, said it. Okay, great. So here's a situation. K is just some field, any field characteristic, not 2. And F of X is an irreducible quartic polynomial that's separable, right? It's got distinct roots in its splitting field, which I am dubbing as capital F. So, finally, I'm going to say G is the Galois group of F of X, which is the Galois group by definition of F of K. So that's my notation that I'm freezing for a moment in time. But 8.56. Using this notation, we're going to let Ri denote the roots of F. Roots of F in capital F. And I want to build a special thing here. There we go. You know, you might go home and play around with this, 'cause it's such a kind of fun to figure out how this works, but my notation, I hope you have an idea. Probably. By the way, any ideas? What motivation? Right. So basically think of this is 1, this is 2, this is 3, this is 4 in this notation, right? Notice that what happens is, for example, this right here stabilizes this, right? And what does it do to this? It flips out the 1 and the 2, and it flips out the 3 and the 4, right? So it stabilizes this, and this one flips out. This swaps the 1 and 2 and 3 and 4, so it stabilizes that as well. Notice that these elements are set up to kind of play off of this here. So let me make an observation about this. The field K, adjoining alpha, beta, and gamma, corresponds to the normal subgroup D intersect G. Right now, of course, whatever the Galois group is, which we're calling G, this thing is a normal subgroup. That's 4, and so its intersection with G would be a normal subgroup of that. So is Galois. Okay. Because of the normality of that subgroup, and its Galois group is isomorphic G mod the intersection, because that's normal G. Okay, we're going to use this lemma in a moment, but because this is, I mean, what this lemma is going to allow us to do is bootstrap this business. So I need to make one more definition before I give you this cute little result here. Yes.
What do you mean by corresponds? Corresponds. When you first wrote that, I thought you meant as in
The Galois correspondence. Right.
but you have up there, it's B intersect G, and down here it's G over B intersect.
So
So which-
you're getting confused about Galois over this. This field is Galois over the base field.
Okay.
Right, so let me draw a diagram. And here's the term, wasn't. Right, now the Galois correspondence is G and this is the intersect B. And this is the identity, right? These are this is the fixed function, right? So that's the correspondence. This is normal here. So remember the Galois group of this over this is this mod this. Right. That's how the Galois correspondence works is if you want to have the Galois group of this over this, it's actually this mod this, right? And that's why this needs to be normal. One of the conditions for this extension here, F is normal over every intermediate extension, but the intermediate extensions are Galois over base field, if and only if the fixed field is normal in this. Right, and the resulting Galois group of this over this is this mod this. That's what the fundamental theorem of Galois is. Is that right? Yeah. So go back to those notes. You'll see that's statement there. So the Galois group here is isomorphic to G mod the intersection. And so, like I said, I think we can use this to bootstrap. Let K be a field. Proposition. Continuous field, and let F be solvent or be the polynomial. Okay. Now, from this polynomial, so if I walk up to you on the street and give you this polynomial, it's monopolynomial according, I can define another polynomial that's cubic that is related to this in a certain sense, and it's going to use this result here bootstrap. The resolving cubic so the resolving cubic is x cubed squared plus AC minus 4D x minus a squared D, so it's plenty constant, minus a squared D plus 4BD and this is actually equal to so I'll save you the misery of looking through it. If alpha, beta, and delta are these three things that are defined here, then if you troll that mess out, and bless your heart if you do, you will get this resulting cubic. And notice this resolving cubic is also in KX. It's not so obvious from here because it's alpha and beta and gamma. Maybe they're not in KX, but when you multiply this all out, notice that of course all the coefficients are in K, so you're good to go. So here's our big theorem on doing coordinates here, and then we'll apply this. So theorem. Theorem 858. Supposed to be a field. I want my characteristics number 2 again. And F X K X separable and so I want this thing to be irreducible, and I want it to have the same roots. Probably have to do this forward. With Galois group of F of X. We'll call this G, which is a subgroup of S four. In fact, a transit subgroup of S four once again. Okay, so here's the setup. You've got a field, characteristic not 2. Actually, I get 3. Anyway, K is field, F of X and KX separable, irreducible, up to degree 4. And the Galois group, we're going to call the Galois group F of X G. Remember, that's the Galois group splitting field. And this is it should be a transit subgroup S4. But alpha, beta, gamma as before. And these are, of course, the roots of the resolving cubic. Now, and of course, alpha, beta, gamma are explicitly these things. And this is how they're related to the roots of the polynomial, the master polynomial of degree 4. Finally, by the way, what are our choices for this? So this is a number, right? It's the degree of the extension of K. You join those 3 roots of K. What are our choices? What's the basis? We do fraction. That's right, 3 factorial. Right. So this, remember, these are the 3 roots to a single cubic polynomial, right? So worst case scenario, you've got Galois group S3, which is 6. 1. What if that's actually got Galois group? What if the resolvent has S3 is this? degree of that distinction is 6, if and only if G is isomorphic as colon. 2. So now that's the biggest you can be, right? This is a cubic extension. What else could happen? Well, it could have Galois group S3. If and only if G is isomorphic to this point of surprise A. What other choices do we have? I mean, it may be the case that alpha, beta, and gamma are already in K in the first place. What if these are already in K? What can you say about the Galois group? Right. Because what you're saying is these are in K, and so they're fixed by all of D. Right. There's one more possibility. Sort of. Oh, but Jim, how can this be? Because after all, this sort of corresponds to the Galois group of resolvent being S3. This is A3. This is sort of trivial. Or the possibility we have. Working out. It could be 2. Right, the extension could be a degree 2 because maybe the resolved qubit, for example, maybe one of those groups is already downstairs. Maybe alpha is downstairs in the field, and then you only have to go up. For example, maybe like 2 conjugates, maybe there's a irreducible polynomial degree 2. However, this one bifurcates in 2 cases. If and only if G is isomorphic to D4 or C4. So this one is either cyclic or 4, or it's the dihedral group on the square. And how do you tell? And D4, if and only if what's the result there? If and only if F is irreducible over this field. So n equals 2 if and only if the Galois group is D4 or C4. And the way you make that choice is it's D4 if and only if F is irreducible over right, if F is irreducible over that intermediate field K alpha beta gamma. So let me give you, I'll work through this next time. And we'll finish this up next time. By the way, I will be assigning your next homework on Friday. I decided that this morning, I guess, quite be convenient. Because I want to get kind of a foothold in the fields. Here's an example for you to work through. Oops. Over Q. So these are all polynomials of Q of the following polynomials. X to 4. Well, 4x squared plus 2. X to the 4 minus 2x squared plus 4. And x to the 4 minus 2. You should actually get different Galois groups for each of these. See if you can figure out what they are, and we'll hit this again tomorrow. Any questions? Yeah, tomorrow I'll give you an amusing story of why not to ever take a negative test. Any questions? All right, well, y'all have a good one and we will